All right, here's a video for class 4, which I'm going to miss while I'm going to Ohio. We're going to talk about pressure vessels. This should be review from mechanics and materials. And we're also going to talk about 3D's Mohr circle, something that usually is not captured in mechanics and materials, but is important in elements of mechanical design, which is the name of this class. All right, just in case you're not familiar with what a pressure vessel is, various things, like it could just be a tank. Of course, it's under pressure, like the name says. Heat exchangers are examples. Piping is an example. Boilers are some of the most common pressure vessels that you'll see. Now, I am going to move over to OneNote because I can't figure out, and apparently no one else can in the world. It's just too complicated to figure out how to get those stupid squiggles to stop in when using Camtasia and PowerPoint. So here we go. Again. So let me see here. I'll go green. All right, so just a quick introduction to pressure vessels. An interesting thing, sort of like the beginning of very formalized engineering, and especially engineering codes, came about because of pressure vessels and explosions that took place in the latter part of the 19th century. We had a lot of locomotives, and we wanted to get more and more power out, so they increased the pressure in pressure vessels, and people were just building these things, and they were exploding, and they weren't really applying engineering to them. So we started having standards, really came out of pressure vessels. So it's a pretty important thing as far as the history of engineering. Now, I'm going to go ahead and try to organize this. I recall people having some confusion, so I'll try to clear that up. First of all, there are 3 kinds of pressure in pressure vessels, right? So 3 kinds of stresses, I should say. I'm sorry, I said pressures and I meant stresses. And so they are tangential. I'll just write tang, aka hoop. All right, so this is probably the most important one. This is the one that what you can think of as the ring is a cross section of a cylindrical pressure vessel. The ring is trying to get bigger, just like a hoop. And if you were inside a hula hoop and pushing outwards, you would be trying to stretch and make that hoop bigger. So it would cause a tension, and over here is the figure from Shigley, which you should buy. You would be causing a tension as the internal pressure. We're going to ignore the outer pressure here. We're just only going to have internal pressure. Pressure vessels is the only one we'll talk about. That inside pressure is trying to make this hoop bigger, and therefore, if you were to cut this off and look at the internal forces, you would see that's causing tension and trying to make it bigger. So that's the tangential stress. We also have longitudinal, which we'll call sigma L, right? And I'll go long O right there. So that's longitudinal stress. That's trying to make the pressure vessel longer. And it doesn't show up in these cross sections, right, of views. It would instead be like if there's an end cap is probably the way to think about it. If you have a pressure vessel that is long, like this right here, right, and here's the end, and inside right here we have pressure going in every direction, but that pressure is pushing against the end of this, trying to stretch it out. Therefore, that stress is on that cross section and coming out of the plane in these views right here. It's coming towards you. And that too is causing a tensile stress. And lastly, we have radial stress, sigma R. And radial stress is caused because there is a pressure right here that's pushing against this stress element. So if we were to put, like, say, a stress element right here, and we were to look at him right here, there is a pressure on that side. So there must be an equal and opposite stress, and that's the radial one. That's the radial direction of that on that stress cube. And it gets smaller as you go outwards till there's zero at the end, which makes sense if the pressure on the outside is zero. So for, let's say, that little cube right here, his pressure is zero, therefore his radial stress is zero. So this curve right here, let's change to red, shows the pressure, the stress distribution as it's going across the cross-section. Similarly, we have a stress distribution when we're talking about a thick-walled cylinder. We'll have a stress distribution where the highest tangential stress, or hoop stress, is towards the center, and the smallest is towards the outside, but it doesn't go to zero. Okay, most of the time, and this is sort of forecasting what we're going to do, a lot of times we will just go ahead and say, and take the average right here. So like the average stress in the tangential direction. And that's a much simpler equation. So the equations that we would be concerned with here, so I guess I'll write it along the bottom. For tangential stress, the equation is R, the internal radius, divided by the external radius squared minus the internal radius squared, times pi, that's the internal pressure, times 1 plus rho squared, the external radius, divided by r squared. Now you notice that r squared, that's the only one that doesn't have a subscript. Okay, so what this is really describing is the distribution as we move in the r direction, right? So we have, this is a radial component right here. We have an r that's to a miscellaneous spot right here. That's just the generic r. So this describes a distribution. And you'll notice that it has pressure right here, right? So the rest of these r's, they all describe the really the distribution. And you notice that the units will all cancel out. And so the only units you have left are, so let's say PSI in American units, which PSI in pressure, but PSI in stress. So you can see how that they're related to each other. So this is hoop stress, and that's the way I'll refer to it probably more than any other time. And this is equation 350 in Shigley. You'll also notice that when when the R is equal to RO, this just comes to unity. So you have 2 times this little chunk right here, right? So this becomes 2 when R, oops, that's terrible, I'm writing here, when R is equal to RO. Let's see other places I can write this. I guess I'll go longitudinal. Okay, longitudinal stress, sigma L, is going to be, I guess I'll write it in the same way, Ri squared divided by, once again, Ro squared minus Ri squared times Pi. And then once again, notice that that this is just a multiplier. These R's dimensionally will cancel out, so that we have like just a multiplier times the pressure to tell us what the stress is going to be. This will make a lot more sense when we see the thin-walled version. Of course, this is the thick-walled version of these equations. Sometimes we'll use these. Most often we'll use the thin-walled equations, which are much simpler. And, okay, so, by the way, this is equation 351, excuse me, 351 in Shigley. And lastly, okay, so we have covered this is the longitudinal we've covered the hoop, and now lastly, we will go with the radial. So the radial stress is going to be Ri squared, Ri squared divided by Ro squared minus Ri squared times 1 minus Ro squared over Ri. Nope, not Ri, but just R. Okay, R squared. So you can see, and this right here is grouped together with the tangential one in the book. So it too is equation 350. But you look at the book and you'll see that it's they're right next to each other. That's why they're. Notice, once again, like I mentioned, that when RO is equal to 0, right? So when you're on the outside, when this guy right here, that R becomes RO, that this sigma R at RO is equal to 0. Okay? Also, it's good to, at this point, to compare the radial and the hoop, and you'll notice that they're pretty much the same, except that one has a plus and one has a minus. And then also in the radial, notice that when R is equal to Ri, right? So I guess maybe actually this would require a little bit of algebra to be able to do this. So it's not necessarily obvious. But so when R is equal to Ri, you end up getting negative Pi, right? Which makes sense that it's negative because it's a compressive stress, right? We're looking up here. We have, on the inside, there's compression from the pressure. Well, there's compression from the stress on the other side of the element. So these are really good ones to know, to be able to pick apart and understand what they look like. And once again, just to emphasize, when we have this, let's see, I don't know what color to pick. I'll pick black. This guy right here and this guy right here, those are variables, whereas the rest are just set depending on the geometry. So that those variables, they decide what the distributions look like. And they're a little bit different from each other. Okay, so now thin-walled pressure vessels, which, once again, this is probably the most common equations that you would see. There's a lot of details going on with the thick-walled ones, but the thin-walled, they make an assumption that pretty much across the thickness of the piece, you're going to have sort of an average or pretty much an even distribution of pressure. So you really use those on the longitudinal and hoop, not so much on the radial. Remember, the radial has a large stress on the inside, 0 stress on the outside. So for the hoop, this is worth doing a quick derivation. And just to give us an idea, just to reinforce what these stresses are, right? So the derivation is really just a force balance. And so if we were going to have, so we take a look at the hoop first. No, excuse me, I misspoke. This is the longitudinal. So what we do, just with every stress, remember that stress is the distribution of force throughout a piece. Usually we can, as the most basic stress, think of force over area. But in order to do that, we need to cut the pressure vessel apart and look inside to see the stresses that are in there. So if we were to say, well, on this face right here, we have a force P that's going to be the pressure times this cross-sectional thing, okay? So we're going to go in the X direction here. So we say, okay, well, we have a force going in that direction, and opposite to it, because we've cut the piece, is the internal forces throughout the thickness that are resisting it. And that's the longitudinal stress. So those forces, let's say that we did the sum of the forces in the X direction. It's going to be static. It's not going to be moving, so they equal to 0 right here, right? we'll say that that's plus, we would say that in the positive direction, we're going to have this longitudinal stress, and it's going to be multiplied by, and I'm going to have to try to do this cross-sectional area right here, right? So there's a stress that's acting on this relatively pretty thin little piece, but it's got this cross-sectional area to it. So we'll say we know that that's going to be the area of the wall, which is we could find to be the diameter or the circumference. Let me say the circumference times the thickness will give us that area. The circumference is going to be pi d, and the thickness is t, right? So this right here is the area through the wall, and minus, because it's in the negative x direction as we're having here, we're going to have that pressure, internal pressure, we could write it, times the pi r squared equals 0. In fact, well, let me use diameter instead. Pi over 4 diameter of the thing squared. Okay? Now, we can cancel a bunch of things out here. To make our lives easier, we could go and we could say, oh, the pi is going to cancel out on both sides. The diameter, one of the diameters cancels out, right? And what we're left with now, if we solve, we get the longitudinal stress is going to be equal to the pressure, the internal pressure, times the diameter divided by 4 and the thickness. Okay, so that's a much simpler equation. This is the one, if it passes a certain criteria of saying, hey, if this is a thin-walled pressure vessel, this is the one that we would use for longitudinal stress. Similarly, we could deal with hoop by cutting it now. Instead of cutting it this way, we could take a section. There's my dog who wants to bark at you. We could cut a piece right here, and not only that, but we could also cut it along through the length of the thing. So now we have pressure in the z direction, and we could take a sum of the forces in the z direction. So sum of forces in the z direction is going to be equal to 0. And I guess the way that we're drawing it here, that's the z direction is positive right here. So we'll take the stress right here, because once again, the hoop, which I'm going to call T, right? That's the same thing as hoop as they've drawn it right here. This picture is out of Philpott, by the way. We use the area, the cross-sectional area, let's see, that's right here. All right, so that cross-sectional area through the cut of the thing. And so that's going to be two rectangles. There's 2 of them, right? So there's one at the top and one at the bottom. So 2 times the length times the height, which would be delta x times t, right? Does that make sense? Yep. And so that's stress times this area. That's going to give us the force in the positive z. In the negative, we're going to have the internal pressure, pi. They're showing it as pz, but it's, oh no, okay, that's their force is what they're calling it, pz. But this is supposed to be a lowercase p. There's the internal pressure times this face right here, across that whole face, which is going to be, okay, it's going to be, I'm going to use diameter. So it's that rectangle, it's going to be the diameter times delta x, right? That would be the area of this big rectangle right here. And that's going to be equal to 0. Now we take a look and we can go start crossing things out. We say, oh, okay, delta x, that was arbitrary, so it's nice that it cancels out. And what we're left with is that tangential stress, and this is going to be actually average tangential stress, is going to be pi times d divided by 2t. These are much simpler equations, and we're going to be able to think of these or use these maybe as a way, even when we have a thick-walled pressure vessel, as sort of a sanity check that we went through and calculated them correctly. We'll notice that the hoop stress is twice of what the longitudinal stress is going to be, because you have 2 in the denominator here and 4 in the denominator, so they're going to be twice as much. And so we could summarize, I think. Okay, so here is a graphical depiction of this, that on the outer part, right here, we have a little cube, and the radial stress is 0, whereas the longitudinal and hoop, if you take an approximation and say, they're just pretty much the average. The longitudinal is always going to be this. This is an approximation. Because if you say on the inside, it's actually going to be somewhat different from this. The hoop, this is, of course, this is the average across, because we already know from the thick-walled pressure vessel right here that it's actually is a distributed thing. It's not the same on the inside as the outside. But the longitudinal is the same on the inside and the outside. Once again, this is an approximation. And on the inside surface, the stress is compressive as equal to the pressure. So the other two, the hoop and the longitudinal, as long as we have a positive internal pressure, those are going to be in tension. Now, of course, you could have a vacuum that would cause compression. Or you can have external pressure, and that would also cause compression. But just to summarize right here, and to make something clear, because the book doesn't use this equation. I think they might use radius, but they don't do this equation right here. They decide for some reason to go ahead and add in the thickness and give you sort of a maximum. So it's a little bit unclear. I think I'll always accept these if it's a thin-walled pressure vessel and we use this approximation. I'll always accept it because it's the most commonly done. If you see it in other books and other places, these are the equations that you'll see. So just to summarize here, we have these three stresses: hoop, longitudinal, and radial. And I'll often write T for tangential just to be in common, and I'll put a little approximately pi times d divided by 2t. Longitudinal, sigma L, I'll say approximately because that too is an approximation when it comes to thin-walled pressure vessels. 4t, and then sigma r, and this is only on the inside, is equal to pi. I left the i's out. And the dog's barking at somebody. It's outside. Don't worry, she's not ferocious. In the book, you will see this right here. The maximum hoop is equal to pi times di plus t. They just make a distinction, and if I am to use this d, I mean the outer diameter. So what they're really doing right here with the inner diameter, adding the thickness, they're really sort of giving you the average diameter. It's totally okay to use this equation. When it is a thin-walled pressure vessel, it does not really change the answer all that much. All right, so this is equation 353. And then also, let's see, the longitudinal, they use this same equation that's on the left here. That's equation also 353, just to make things nice and confusing. And okay, so this is, I'll write this, is on the inside, and r is equal to 0, the sigma r on the outside. Now, the question should come up, okay, so this was actually, I meant to write this on your page right there. So we asked this question. It's an important question, and happens a lot in engineering. When can you use an equation? That's one of the reasons why we have these classes, right? One of the reasons why you're not just learning things out of a book, because there's a tendency as an engineer just to pick out equations out of a book. But we always want to try to contextualize everything. We always want to have be investigators and take a look. If we have a situation, we have to be very sure that whatever we find in a book is exactly matches our situation. So we have to have these types of, always be on the lookout for these types of criteria. So when can I treat it like a thin-walled pressure vessel? When the thickness is less than 1/10 of the radius, right? So you want to see page number 128 in the 10th edition of Shigley, and that's going to be the first sentence of the thin-walled thing. Will tell you, right? So we want to be, that's a test that you want to arrange. Anytime you're looking at a pressure vessel, take a look at the radius. Okay, you might ask, is the inside radius or the outside radius? Either or, doesn't really matter. You're rarely going to, end up with it's going to be like right on the button. If it's right on the button, you might want to be a cautious engineer and calculate it both ways just to see. And also a curious engineer to calculate it both ways and see what the difference is, give you a better sense of what's going on. So here's an example I put together, I got this out of Philpott. Okay, so it's an aluminum scuba diving tank, and they gave us the dimensions and the wall thickness, and it has air, and they tell us what the pressure is. And so we want to find the hoop and longitudinal stresses based on the thin-walled assumption. The normal stresses on a stress element on the inside, all right, of the thick-walled, right? And so we want to do the thin-walled approximation, the thick-walled, and we want to compare. I like to ask the compare. Anytime I ask a compare problem, that means I want a percentage. I want a statement that says this one is bigger than this one, this was this much more smaller than the other one, whatever. I want you to come to some conclusion. So let me summarize to write them in radial form here, because that's what the thick-walled equations look like. So the external, the outer radius is 175 divided by 2, so that's 87.5 millimeters. So let me take a look at the ratio of the radius to the thickness. That's 12 millimeters thick divided by 87.5, so we get 0.1371. So we're kind of on the button here, right? So this is technically not a thin walled. We'll go ahead and use the approximation because we were told to, but it's worth noting that, hey, yes, we would treat this according to our criteria as a thick walled pressure vessel. Just to check the inside radius, well, I haven't written it yet. The inside radius is going to be, well, we could find that it's going to be the outer radius minus the thickness, right? You always have to do a double check here. It's really easy to get that confused. Sometimes people think, hey, do I take 2 times the thickness or 1 times? If you just use the radius, it's a lot easier to rationalize that how many times of the thickness you need to remove from the thing. But we have 75.5. is what we end up finding, 75.5 millimeters, and that ratio is 0.1589. So you'll see that that too is greater than 10%. So yes, it's a thick wall. I think in some of our equations, we're going to want to know what DI is going to be. We know that's going to be 2 times the internal radius, so 151.0 millimeters. Yeah, so because units cancel out in this case, I'm going to go ahead and use millimeters, but most of the time I turn things into base units when I do calculations, so this is an exception. So here I will find the hoop stress from my basic equation, PID divided by 2T, and I've decided to use the outer diameter because that's usually how people refer to things. And so 18 megapascals times 175 millimeters divided by 2 divided by 12 millimeters. Once again, we'll notice that the units here cancel out, so it didn't matter that we were using them. We'll then get 131.3 megapascals in tension. Let's go ahead and check what the maximum is going to be, because that's the equation that's in Shigley, and probably the one that you'll gravitate towards. That's PI times di plus t divided by 2t. You'll have, once again, I'll leave out units because we already know them, but that's 151 plus 12 divided by 2 divided by 12, and we get 122.3 megapascals tension. And you'll notice that there's there's a 7% difference in our check, right? I'm just being thorough to check both of them. Also, we want the longitudinal stress. That's just going to be pi d over 4t. And honestly, we could have just divided this hoop stress that we had from the beginning at the top there by 2, because that's what the equations are. Only one half of the other. So we end up getting 65.63 megapascals in tension. And if we were to use the internal diameter instead of the external diameter, we would get a smaller number of 56.63. It's a 16% difference. I don't think that's an accurate value here. But we could check in a minute here against the thick-walled. Okay, so these are the thin-walled solutions to this, or the hoop and the longitudinal stresses based on the thin-walled assumption. Okay, so I need more space over here, so I'm going to go over to the side. I should have made another slide. All right, so part B here, we're going to do the same thing, but we're going to use the tangential, or the hoop stress, and we're going to use the RO squared pi divided by RO squared minus RI squared, and 1 plus RO squared over R squared. And what did we decide? It's going to be on the inside. So we decided we wanted to be on the inside of the tank because that's where the maximum stress, the maximum hoop stress is going to be. If you remember this diagram up here, remember the maximum hoop stress is on the inside. So that's a good place to check. It's actually good to check on the inside, on a element on the inside and the outside, to be thorough. All right, so we take and plug the numbers into this. So we get the 75.5 squared, that's the outside, times our 18, divided by our, did I get that right? Okay, no, that's the RO. Did I do that right? RO. I think I calculated this wrong. Go figure. Or maybe I wrote it incorrectly. Let me see. Let me double check here. Come back. Oh, yep. Okay, RI. So I wrote it down incorrect on my sheet. So where did I go? All right. So I wrote it down wrong here. There you go. That's RI. Need to be PI. All right. So I gotta fix that. Okay, 87.5 squared minus, that's a squared, minus 75.5 squared. 1 plus 87.5 squared divided by my 75.5 squared. And I end up with 122.9 megapascals in tension. Notice, compare that to what we had over here. We had the maximum according to the Shigley maximum for the thin walled was 122.3. The maximum according to the thick was 122.9, which ends up being a 0.5% difference. All right. Our approximation for the in the standard way, in the way I call it standard, the way that you most often see in textbooks, the simplified hoop stress, That's a larger number. We usually use a phrase that we're being conservative when we can choose something like that. We can see, even though there's a difference, it's like a 7% difference between these two approximations. It's a larger stress, so we're being more cautious by assuming the stress is larger. The longitudinal, the version of this is, I think I'm writing it wrong. I think it was RI squared and then PI divided by RO squared minus RI squared. You can plug numbers in just as easily as I can. So if we do that, 52.46 megapascals in this in tension. And we'll note that that's an 8% or about an 8% difference. And in this case, it's less again, right? So we had 52.46. Our approximation with thin-walled was 65.63. We have a lower, but it's difference, and we'll say that it's less, which is important to note. And then lastly, the radial is just going to be, and I don't want to write it negative, I'll write that it's 18 megapascals compression, right? And then the last thing I want to do is summarize is that the thin-walled approximation is approximately 0.5% greater than thick for hoop and approximately 8% greater for longitudinal. And I'll be lazy and just write long. So I don't want to make the video long. It's already going to be too long. All right, so that's a pressure vessel. And one of the reasons why I've grouped that topic with the general three-dimensional stress, where we're going to learn this next and important distinction between regular plane stress, is that this situation with a pressure vessel is one of the few times I can think of when we can, by hand, calculate a stress scenario where we have all three directions. All right, so internal to parts, yes, you will have stresses in many different directions, but most of the time we're actually looking at either a surface stress. We're looking at a stress element on the surface. It could be on the inside surface of a pressure vessel, which is where we find the three different directions, the three orthogonal X, Y, and Z components of stress. So something right here from this figure, you'll see that there's a more complicated Mohr circle where we have two Mohr circles inside a larger Mohr circle. So I'll make this statement that every stress has three components to it, but most often the case is plane stress. One of those three principal stresses is zero. We'll also make this very important thing that we always use the convention where we have principal stress 1, 2, and 3, and 1 is the largest and 3 is the smallest. So if one of the stresses has to be compressive and the rest are tension, or 1, 0, the one that's in compression with the lowest number, right, is principal stress 3, whereas principal stress 1 is the largest, and it could be that they're all three of them in some scenario. Maybe it's at the bottom of the ocean, right? So you have pressure on all 6 sides. So you have 3 compressive stresses. The one that's the least negative, right? So actually, I guess you would say the maximum, that's still the first principal stress. So there's arranged in descending order. Now, I want to prove to you that there's always three principal stresses. I'm going to do that with a couple scenarios here. First, the scenario where we have a stress, let's see on here, where we have 60, could be PSI or it could be megapascals. It doesn't matter. I'll have tension in the X direction. I'll have compression of 60 in the Y direction, and it'll be 0 in the Z direction. So this is going to be the plane stress condition. And what we'll do is I'll say, okay, well, take a look at the face that's on the X, that the X direction is normal to, and we'll call that the X face. And what is the stress state on that? Well, it's just going to be 60, right? There's no shear here. So what we actually find out is that that's one of the principal stresses, because principal stresses have 0 shear. So that's one of the principal stresses. So this right here could be, is not only sigma X, but it's also going to be, well, I'll label it in a second. And then, in the other side, okay, we'll call it the Y face, is going to be negative 60. So this is the location of that stress. If we were to draw a Mohr circle here, we'll see it's a Mohr circle that passes and comes up 60 through here. Boom. So this is our Mohr circle. All right. So let's take a look. This scenario that we just drew right here, if it was plane stress, would be with the looking down the z-axis, so it would be at the top right here. So we can summarize that the Mohr circle we've just drawn looks like that right there, 60 and 60, right? You don't have to put a sign next to that 60 because it's the arrow shows that it's compressive. All right, so now let's switch and let's look at the face that's in the YZ direction, right? So now we're going to be taking an eyeball and looking this way right here, right? So this is our creepy eyeball, and he's looking at that face, and all you're going to see in that face is the 60 compression. There's nothing in the Z direction. So if we were going to take a look, so in the Z direction, this is the face. That's the plot point that we would be making off the Z face right here. It has 0 shear, 0 stress, so that's the plot point. In the Y direction, that's still this plot point. So we have another Mohr circle represented by this stress element in the plane stress, looking at it as if it was plane stress. That's the Mohr circle. And then lastly, we take a look and do it in the XZ direction. Now we're going to be looking down from above right here, right? So we're looking down this way, down at this thing, and all we would see is tension of 60 in the X direction. So once again, we plot the Z face right here. We plot the Z face point, once again 0, and we plot the X face, and it's right here. So we have another Mohr circle right here. So the principal stresses in this case are sigma 1 is equal to, so we go sigma, that's a 6, not a sigma. Sigma 1 is equal to 60 in tension, right? Let's write tension. I'm just leaving the units as whatever they happen to be. And then same thing for sigma 2 now is going to be 0, okay? Because this is sigma 2 right here, and this is sigma 3. Sigma 3 is equal to 60 in compression. I'm going to do another one, similar idea. Let's beat this dead horse to death. And in this case, I'm going to have 20 and 80, right? So there's still 0 in the Z. So looking at the plane stress faces here, we have 20 and 80 there. So we plot that Mohr circle. We get 80 and 20 right here, right? And so if all we were looking at was 2 dimensions, that would be the plane stress. Now let's go to the YZ face. So we're looking at from this direction right here down the X axis, and all we see is 20, right? So, and then the other face would be 0. So we would have these 2 points right here. So we get this itty bitty Mohr circle. Do the same thing for the XZ plane. Now we're looking down at it again, and we see all we got is 80 in this direction. So 80, that's the plot point here, but this other face, we want to plot that to get a complete Mohr circle. So we have this right here. And we're really doing this for a very good reason. It might seem kind of trivial at this point, but it's really to protect us from making a mistake. And that's because now all of a sudden, if we were in this condition right here, and we were to be asked, what's the maximum shear stress, that maximum possible shear stress from this configuration, it would be right here. This would be the max, right? But it would only be the max for this stress condition, for that plane stress. The absolute max actually comes from this and would be like right up here. And so the max, or often I will call this the abs max. And if I ask for maximum shear, this is the one I mean. I don't mean this one. Right? Because there could possibly be a maximum for this one as well. This one has. And a lot of times we will refer to these, right? Another way of writing this is, because this is sigma 1, this is sigma 2, and this is sigma 3, we could say that the maximum right here was 1, 2. I can't remember if I put a comma in here. And what I mean is, this is what the tau 1, 2 is going to be, right? And this guy is, this abs max in this case right here is actually 1, 3, right? So that's sigma 1 minus sigma 3 divided by 2. And then we can also have sigma 2, 3, which is what this guy is, sigma 2, 3, which is, tau 2, 3, tau 2 minus sigma 2 minus sigma 3 divided by 2. But the largest of these is always going to be this guy right here, because we established that 1 and 3 are the ones we want to look at. And by the way, this would be the absolute value of it, because it doesn't matter. We don't treat a positive and negative shear. So for our problem right here, I really, if I'm going to be complete, I only write that it's 80 in, we'll say tension here, because I didn't give it a units. I just said it was a number. Sigma 2 is going to be 20, also in tension. And sigma 3 in this case is equal to 0. So that's like a proof, a demonstration. Now, I will leave these for in-class exercises and trials. No, I guess maybe I did these in previous class. So I'll also mention there's a little bit of can be some confusion, because in one part of the book they'll use sigma 1 and sigma 2 to just be the 2 principal stresses when it's plane stress. To avoid this, we're going to say that when it's plane stress, the 2 non-zero ones are sigma A and sigma B, and then we'll decide where they rate as sigma 1, 2, and 3 when we decide which one's going to be 0. Okay, so when the 2 non-zero ones are usually given this way as sigma A. So from the previous example, we had 34.7 KSI. That would be tension that we had. And the other way, let me leave off the tension here, because I'll use positive and negative here. Negative 29.4 KSI is what we found. Therefore, our sigma 1 is 34.7 KSI. Our sigma 2 is 0, and our sigma 3 is equal to negative 29.4 KSI, right? So, yeah, and then so what we would find is our, let's see, let me put these out in here. So we had 0 here. So here's sigma 1, here's sigma 2, and here's sigma 3, right? And now, no, wait, what did I do? Yes, I did it correct. Okay. And we'd find, boom, and then boom. I could have put that sigma 2 in a better spot. So our absolute maximum is actually sigma 1 minus sigma 3 divided by 2, right? Which is what we had before. So it didn't seem like it mattered. Sigma 1 minus sigma 3 over 2. I think we had that 32.0 KSI was the answer. For this scenario right here, we had sigma A was equal to, all right, that's sigma A and this is sigma B, negative 33.1 megapascals, and sigma B was equal to negative 123 megapascals. Well, now we know that sigma 1 is equal to 0, because there's always going to, in plane stress, there's always going to be one that is one of the principal stresses that's 0. In this case, since the other two are negative, this one has to be 0. Sigma 2 is going to be negative 33.1 megapascals, and sigma 3 is equal to negative 123 megapascals, and therefore tau absolute max, right? So let me draw those first before I finish that thought. So now we're going to have a Mohr circle that encapsulates sigma 1 and sigma 2. And here's sigma 3. And then we're also going to have a big Mohr circle. And right here is going to be the tau abs max, absolute maximum. And that's going to be sigma 1 minus sigma 3 divided by 2. But of course we have 0 minus 123 over 2. So we end up with 61.5 megapascals. And if we had not recognized that there are 3 Mohr circles, that one of them is 0, we would mistakenly have chosen that right here as being the maximum shear, and it would have been larger. And that's going to be important to us, because one of the things that we're going to do, I'll tell you ahead of time, that we're going to establish a criteria. One way of one theory of failure is maximum shear stress compared to maximum shear strength. So we would be off, and we'd be wrong by not recognizing there are 3 Mohr circles. Last one quickly, a similar thing. We could walk through these. Sigma A is equal to 73.8 in this case. Sigma B is equal to 24.2 megapascals. We could take those are the non-zero ones, but now we recognize that this is sigma 1, this is sigma 2, and 0 is sigma 3. So sigma 1, 73.8. Sigma 2 is 24.2, and sigma 3 is equal to 0. Draw those on there. Here's the other Mohr circles. And once again, we have a condition where we would have had a too small of an absolute max if we hadn't recognized the 3 Mohr circles. So the abs max is sigma 1 minus sigma 3 over 2, and so that ends up being 36.9 megapascals. All right. So let's see, for our scuba tank example, remember it was on an interior surface right here. So here is the little internal stress element. We had 18 megapascals of pressure, so it's compressive, but we had, let's see, I think this is the orientation that I was drawing here. Right here. So there's a cutaway. So I'm looking at this little piece right here, right? Okay, so so we see on these we have tension here. That's the longitudinal direction. The tension is 56.6 megapascals, and we have hoop, which is going upwards in this case off of that from the cube, the way I've drawn it, and that's 123 megapascals. And because there's no shear, that makes this much easier. Mohr circle, right? That we have, so this is equal to sigma 1, this is equal to sigma 2, and this is equal to sigma 3. So that's going to be right here. There's sigma 3, it's negative. Here somewhere and here. Of course, I haven't drawn it proportionally. I'd expect you to do better than me. Sigma 1. So we have this condition, and this condition. Here's the abs max. So the abs max is 123 minus 18 divided by 2, or 70.5 megapascals. All right. And I think that's all my examples. I think that's the end. All right. So this was a very long video. Sorry I'm missing class, but I'm sure we'll get together and you'll be able to figure out what's going on. So let me try to figure out how to stop. Oh, here you go.